Yeah, and it's our pleasure to invite the three professors in our field to give the presentation today. Please let me give the brief introduction to the three professors. First, we invite Professor Hidetaka Arimura from Kyushu University. Dr. Shier from University Malaya, and Dr. Mazen Soufi from Nala Institute of Science and Technology. Okay, the topic today is the basic and advanced technology of artificial intelligence for medicines. Yeah. So if after each presentations, we have the short time for question and answers. And if you have any questions, please leave it in the chat box. Okay. First, it's my honor to introduce the first professor, Dr. Hidetaka Arimura. He comes from Kyushu University, and his research expertise is medical image analysis, medical physics, computer-aided radiotherapy, and computer-aided diagnosis. And it's our honor. Yes, Dr. Arimura, it's okay?
Yes, sorry.
Yeah, please share your presentations. And the topic of the first presentation from Dr. Arimura is basics of radiomics, AI, and whole analysis. Please.
Thank you very much. Nice introduction during Chinese New Year. So sorry. So anyway, we should celebrate Chinese New Year. Okay.
Yeah.
So let me start. My title is Basics of Radiomics AI and for Analysis. And look at my name. My name includes AI. So I'm very suitable person for explanation of AI. So at first, my outline is here. What the issue in background of medical AI for cancer? I focus on today just cancer, and I'd like to propose for analysis beyond the conventional radiomics and radiodynamics, and the value of radiomics. So how are cancer patients treated? So here is a patient, a cancer patient. So this patient may receive surgery, chemotherapy, or radiotherapy, or immunotherapy. But we have guideline like this. This is a guideline for lung cancer and non-small cell lung cancer in Japan. So if the patient has a stage 1 cancer, this patient may receive surgery first. But if the patient is inoperable or refuse surgery, the patient receive radiation therapy. But we have problem. So here are two patients with similar profiles treated by same radiotherapy. And look at this, almost the same profiles, but quite different survival time, like this. So almost 4 years and less than 1 year. So in this case, we have issue. One size fits all treatment procedures could be unsuitable for some patient. So here is statistics from this paper. This paper, according to this paper, survival time of stage 1A, stage 1B has 60% to 77% for surgery. But almost the same survival time from radiotherapy, around 64 and 76. So this means a standard treatment method is not always effective for all patients. So that's why we, someone, I think, arts proposed a rademics idea, and rademics can help physicians to do personalized treatment approach. Okay, so rademics is one of the omics research field where a set of medical image features related to patient's prognosis consider radiome, like a genome, a transcriptome, and a proteome, and a metabolome to improve diagnosis, treatment, and prognosis. So here is procedure for rademics. So at first you have to prepare the collect many medical images, and you can calculate image features by using usually we use histogram features and texture features or shape features, and also we calculate wavelet features. Then we select features, significant features from all features. And by using these significant features, we classified patients into a low-risk group or high-risk group of, for example, survival times. And this is the basic knowledge for Kaplan-Meier curve. X-axis shows the survival time, and the y-axis shows the survival rate. So here is two Kaplan-Meier curve. This Kaplan-Meier curve shows a low-risk group because longer survival time. And this is a high-risk group survival as Kaplan-Meier curve because this patient has a shorter survival time. And we try to classify patients into low-risk group and high-risk group by using an image feature, significant image feature set. Then we calculate the p-value of log-rank test. If the p-value less than 0.05, the image feature, significant image feature sets may be effective for classification of low and high risk group. And what issue in rademics we considered? We considered at first gene with mutation. This information, gene information with mutation, may be transferred to messenger RNA, and this messenger RNA produce protein and metabolome, and finally we have phenotype of human body. And this information, metabolite information, can be scanned by PET, and we get PET images from this information. And phenotype, final human body, can be scanned CT scanner, and we to get CT images. So this is the assumption. So we assume these medical images include gene information or messenger RNA information or protein information and the metabolite information. So by using RedMX, we can do tumor malignancy, evaluation of a tumor malignancy, or detection of a gene mutation, and to select treatment approach, personalized treatment approach, or prediction of recurrence. These are just example. We have many applications to RadioMix. And from now on, I'd like to propose whole analysis beyond conventional RadioMix. I'd like to explain the background. So here is a typical workflow of RadioMix. We calculate many image feature by using feature model. These are equations for calculation of many image features based on the histogram or texture, and I already explained. And we have disadvantage problem in conventional radiomics. So these are disadvantage of conventional radiomics features. First, interscanner variability. And the second, vulnerability for various imaging protocols or imaging scanner. So we have these problems. So we consider the requirements, two requirements of better features in radiomics than conventional ones. From medical point of view, we need image features which satisfy these cancer phenotype. So cancer phenotype includes induction of angiogenesis or invasion of growth suppressors or resistant to cell death or so on. So first requirement is, sorry, this is a second. And the image feature should be associated with cancer phenotype. And the second requirement is mathematically invariant. So this is very important, but two important features. So mathematically invariant and associated with a cancer phenotype. So we hypothesize topology can produce image features to meet the two requirements. So what is a topology? Topology is so-called soft geometry or geometry of connectivity. So we just consider the numbers of connected components or folds or cavities. So which we don't care. We don't care concrete shapes. Concrete shapes. Here's an example. So very funny face and eyebrow and the eye and the mouth. So we have just 5 connected component. Connected component in this case, white region, just 5. 2 eyebrow and 2 eyes and 1 mouth. So in this case, B0 is equal to 5. B0 means the number of connected components. And mouse has a 1,4 here, black region. This black region 4 does not connected with edge of this image. So in this case, we consider this black region as 4. So in this case, B1 is equal to 1. B1 means the number of holes in this case. And we have another hole in the two-dimensional hole. We have two-dimensional hole. This is a cavity in three-dimensional shape. And here is example in medicine related to the human body. So our bodies are topologically similar to a donut. Here is a initial human body, and here is the initial anus, and this anus became a tunnel until to make initial mouth here. Then we have adult human body, anus to mouth, and between mouth and anus, we have a digestive system. This is a adult human body, but our body are almost the same as like this. Then, topologically point of view, on this human body, maybe donut. So this is a topology idea. We don't care concrete shape. Just in this case, tunnel, one tunnel. And like a human body, we consider the cancer pattern. Idea of whole analysis is classification of object based on number of holes, batch number. So this is the batch numbers. Here is cancer pattern A, and here is cancer pattern B. By deforming this concrete shape of cancer pattern A until this simple shape, and cancer pattern B became to this simple shape. Then we can calculate B0 and B1 batch numbers. So this batch number, this shape has a one hole. That's why B1 is equal to 1. This is a number of holes. And the B0 is a connected component. In this case, gray region has just one gray region. And this is a one gray region here. So in this case, B0 is to 1, and B1, there is no hole. That's why B1 is equal to 0. Then we can classify cancer pattern according to batch number like this. So if the batch number has a B1 is equal to 1, the patient maybe was progress. And this patient maybe better progress. So, but this is just an assumption at this moment. So if we have false, the patient maybe was progress, and there is no fall, the patient maybe better progress. So anyway, cancer patterns could be classified based on batch numbers. But it could be. So, but why do I stick to false? Because I was called Arimura. I was called for Arimura. So by my captain, when I played, when I used to play ice hockey as a goalkeeper, here is me, very young Arimura, in an ice hockey team. So during my student days, I played ice hockey as a goalkeeper. This is not me, but anyway, but as my keeper has a fatal defect, and because I cannot protect puck. Sometimes go through into the goal. So that's why I was called as Paul Arimura. So anyway, I love falls. And this is another topic. Sorry, this is just a break. And you may be able to reduce training cases for segmentation of lung tumors during deep learning. So we try to reduce the number of cases for segmentation of using deep learning until the TTR is 0.116. TTR is ratio of number of cases in training dataset to that in test dataset. We reduce the number of training cases until 0.116. Very few cases, but we have DSC of around 0.8. This is an amazing result. And we have very nice segmentation results like this. So this is a different research from for analysis, but I'd like to introduce. So from I'd like to go back to the for analysis. And are there evidences that cancer has folds? Actually, we have. So here is relationship between cellularity and prognosis. So look at this Kaplan-Meier curve. If the here is a histological images well differentiated and moderate and poorly differentiated. Anyway, if the cancer has a higher cellularity, the survival time, overall survival has a very high risk patient like this. So in this case, high cellularity areas may become islands in tumors binary images. So this is a first evidence related to topology. Islands means connected components in this case. And the second evidence is necrosis and prognosis. Here are necrosis region contoured by a yellow line, and you can notify holes within cancer region. This is a lung cancer region, and this region may be necrosis. And according to this data, if the patient has a necrosis, they have a high risk survival like this. And this is almost the same data. And but Kaplan-Meier curve did not depend on necrosis area. So this result may be supported can be characterized by topology, because topology does not consider area. Topology just consider the number of holes. So in this case, necrosis, number of necrosis. So necrosis area may become holes in tumors of binary images. And this is another evidence. So if the cancer has a cavitation, the patient has a high risk survival like this. And another evidence is from angiogenesis. So here is the images of angiogenesis on the mouse cancer. And according to this result, I thought new vessel is angiogenesis within cancer. Due to angiogenesis may become tunnel in tumors of binary images, but it depends on CT value. And here is a Kaplan-Meier curve. If the cancer has a high MBD is a microvascular density, high mass microvascular density, the patient has high risk survival. So like this is a very strong evidence. And I'd like to summarize for analysis. Medical targets are cancer, in my case, and biological components in histological images includes cells, cellularity, maybe islands in binary image, and necrosis, maybe holes in binary image, and vessel, maybe tunnels in binary image. And topological components, CT images, we focus on CT images or sometimes MRI images. And anyway, cells become islands, and necrosis may become holes, and the vessel may become cavity in the topological components. And here is overall scheme of the whole analysis. At first, we obtained the binary image like this. So we focus on this area, and we calculate force in this case, connected components, number of connected components, and the number of holes. So in this case, we have just one number of connected component. Then B0 is equal to 1. And there are 3 folds. That's why we have B1 is equal to 3. Then we can calculate all batch number in all area. Then we have B0 map and the B1 map. And additionally, we calculated the B1 over B0 map. Then here is very strong evidence to classify the patient by using topological image features. According to this result, very low p-value by using topological features. But deep learning shows no significant difference between 2 Kaplan-Meier curve, low risk and high risk in the test group. Then time is running, so I'd like to faster speaking. And another idea, this research, sorry, I'd like to explain the background. EGFR mutation. We try to detect EGFR mutation by using a topological invariant batch numbers. And in this study, we use topology and sorry, this is sorry, this is a different. This one, sorry, this one. And we have background, and in Asia country, we have many EGFR patient, mutant, many EGFR mutant patient. So in Asian country, so that's why we focus on this detection of EGFR mutation. Then we calculated the batch number map like this. And we have very nice result, AUC of sorry, this is the test. Here is a test 0.77 from batch number to detect EGFR mutation. And go back to, oh my God, I'd like to skip, sorry. And this is another topic to detect subtype of EGFR mutation and radiogenomics research. So to detect DEL19 and L858R. And in this study, we use three-dimensional topological fold analysis. So here is topological analysis, but three-dimensional fold analysis by using homology theory, very complicated theory. So in this study, we receive support from mathematicians. And but we have very nice result. AUC, this is the test result. AUC was 0.839 and or 0.87 by using three-dimensional batch number or two-dimensional batch number. And subtype classification, we have this result 0.739 or 0.76. These were higher than conventional study. And another topic was prediction of radiation pneumonitis by using, in this case, also topological image features for analysis. So we have many patients with radiation pneumonitis like this. So we'd like to predict radiation pneumonitis before treatment. So we calculated batch number within lung region, and we add KL6 information, and we have very nice result for validation test. Sorry, this is a validation test. And we applied whole analysis to the prediction of malignancy grade for parotid gland cancer and to the prognostic prediction for head and neck cancer. And also we applied for analysis to the prediction of primary sites of brain metastasis. So we published 8 papers so far regarding to whole analysis. And this is the final slide. We thought non-invasive rapid low-cost medical images can be used to obtain the information necessary for personalized treatment by using radiomics or radiogenomics. And radiomics and radiogenomics can assist in treatment by establishing AI models based on image features associated with prognosis. Thank you very much.
Thank you, Dr. Arimura. It's a very great presentations, and we have still another 10 minutes for questions and answers. There is a question from Dr. Diksha Jaiswal. And the question is, how can we apply radiomics features in our routine? What are the ways to implement it? Yeah, it's really a question. I also have this question as I think most of our researchers. Yeah.
For example, in Japan, we cannot apply because we need a permission from government to use software, clinical software, software in clinical setting. But in your research, you can use radiomics features by using such as pyradiomics. Do you know pyradiomics? Anyway,
Yeah.
you can use pyradiomics.
Do you mean that
Library.
is a commercial software to
No,
analysis?
not a commercial software. I think so far we don't have commercial software of radiomics. Just a research phase. So you can download library, radiomics library from pyradiomics.
Okay.
So
Yes, I think the pyramid. I think there are a lot of evidence to show that there are strong relationships between the radiomics features and the diagnosis and the treatment outcomes, just as you presented. But we know the radiomics has been started for more than 10 years, but after this long time, there's still no commercial software to give the applications in the clinical routine. I think maybe there are some reasons. For example, the stability or the reproducibility for the images and the also for the radium mix features.
That's why I proposed another features because the conventional radiomics features has a vulnerability or very unstable. So that's why I try to search the another features like topology.
Yeah. And we also sorry, please. Yeah, please.
Sorry, we receive comments. I think the reason is that we need manual work to label some features. Yeah, but I think problem is medical doctor hesitate to use hesitate to predict cancer features, cancer prognosis using commercial software. So if the medical doctor hesitate to use such radiomics software, I think manufacturer don't want to produce, don't want to make such software. I think so.
Yeah. Okay, thank you. Okay, any more questions?
I don't know.
Okay, thank you, Professor Arimura.
Thank you very much.
If you don't mind, we move on to the next topic.
Okay, yeah, please.
Thank you. Yeah, thanks for Professor Arimura's presentation. And we would like to invite the second speakers, Dr. Shier from University Malaya. It's my pleasure to give the introduce to Dr. Shao. Dr. Shao comes from University Malaya, and she's the senior lecturer department for artificial intelligence, faculty of computer science and information technologies. And the topic of Dr. Shao is basics of advanced AI architectures and applications to musculoskeletal analysis. Yeah, thank you.
That is the third one.
Yeah, hello.
My topic is, hello, can you hear me?
Yeah, it's very good. Yeah, please
All right.
go on.
Okay, can you all see my screen?
Yes, very clear.
Okay.
Yeah, okay. All right, thank you so much for the invitations to allow me to speak in this seminar school. So thanks for the introduction as well. I'll just introduce myself again. So I'm Shirley. So my surname is Saw. Come from University Malaya, Kuala Lumpur, Malaysia. And today my topics is on the basis of AI concepts and applications to health informatics. So just a little bit background of myself. My PhD was from biomedical engineering from NUS, and I did a postdoc which focused on using AI techniques to solve healthcare or biomedical applications. And then just in 2021, I joined University Malaya as a senior lecturer in the Faculty of Computer Science. So my research interest is mainly on fetal health informatics and also apply AI techniques in solving medical problems. So there will be two parts of my studies, of my talk. The first part is talk about the AI. So as you can see from here, AI has been gaining so much interest back in 2022, and then it increases exponentially in 2023. And recently, the most hot topics that people talk about of AI, as we know that it's really the ChatGPT, AI chatbots, and also generative AIs, right? So as you can see from here, Midjourney, okay, is some AI, is a generative AI which produce images, generate images from sentences, which means that you give or you prompt some sentences, and then the generative AI will generate some images based on the sentences. Same goes for DALL-E 3, which is owned by OpenAI, where another very popular applications from OpenAI is also ChatGPT, where you can ask a tons of different questions and it can act like a humans to answer your questions. So a bit of the AI journey from the last few decades up to now. So AI is not that new. It was always started at 1950, right? So it started in 1950, and then along the years we have been reached in 2024, which currently with the advanced computational resources, AI is now have the capability to recognize images, to able to generate sentences that have the same capabilities comparable to a human. Right, so as mentioned, it started in 1950. It goes through some dark ages, which is the AI winter, because during that time, we do not have enough computational resources and also digital informations to proceed. But with the advances of the electronics and computer resources, we are now able to train a very big model, right, with a lot of digital data. So I believe a lot of us hear about AI, artificial intelligence, machine learnings, and also deep learning. So it is important for us to know that what are the differences between these three very popular terms. So artificial intelligence is a big umbrella where it encompasses the technique that enable machines to mimic human behavior, right? And machine learning is a subset of AI techniques, which uses statistical methods to enable machines to improve with experience. So if you look through the articles or any journal paper that talk about machine learnings, they are referring to like support vector machines, random forests, logistic regressions, where the whole idea of those models are using the statistical algorithm. And deep learning is even more specific or specialized, which is a subset of machine learning,
which makes the computations of multi-layer neural network feasible. So, for example, a generative AI like transformers and other LLM big models, which consist of many layers of network that combine together, all these are called deep learning, where you have a multi-layer neural network. Okay, so that's why we call it deep learning. So these are the three common terms that we can always see around us. AI is a big umbrella. Okay, so if we are talking about machine learnings and also other computational works like fuzzy logic and etc., it's considered as AI. But you are referring to for support vector machines, random forest, this is considered as a machine learning. And you talk about AlexNet, computational neural network, CNN, ANN, LSTM, all these are considered as a deep learning, which is consists of multi-layer neural network. So artificial intelligence, the whole idea for AI is it try to mimic human behavior, right? So human behavior lets us just rewind back to the time when we were baby or when we were a toddler. So think about what do we do or what do we learn when we were a toddler, right? If you can spend some time when we were born, when you have a kid, the first few things we teach the kids is really about how to speak, right? How to speak, how to recognize an object. For example, given some apples or chairs, we teach the babies or the toddlers to say that, okay, this is a chair, okay, this is a table, right? So we teach them how to recognize, right? Recognize different objects, recognize colors, recognize digits, alphabets, okay? And we also teach them how to do calculations, teach them how to write, how to speak, how to sing, how to draw, all this kind of thing. So if we translate this to machines, it's really just for recognitions. In machine, we teach the machine how to do classifications, okay? How to do object detections, okay? Calculations, and for write, speak, or sing, so it's a generative AI. Where write, you can think of it like a ChatGPT. It can write a good sentence for you. You give in a very poor grammar mistake sentence, you ask the ChatGPT to rephrase it with a correct grammar, it's able to generate a sentence that is of a good quality sentences, right? I think same goes for singing. There are also generative AI that's research that's being done in the music field. So now that we know that machines and the humans are kind of doing a similar thing, the next thing we want to ask is how do we want to make the machines to mimic human behavior? Machines for computers is nothing but it's all reading in the binary bits or bytes, right? So how do we make all these actions that is understandable by the machines? So before that, when we want to teach the machine, we have to understand how human learn. So human learn via experience, right? So when we were a baby or we were teaching a toddler how to recognize fruits, for example, we will give them a bunch of different examples of fruits, like for example, apple or grapes. Then you will show them that, okay, if you see this kind of red color, circular object, this is a apple. And you bring, when you go out to the morning market, you saw an apple and then you will ask your kids, what is this? So through the different experience, our human brain will be able to identify and recognize that if we look at something like this with a red color and it belongs to fruits and it is this kind of shapes, it is an apple, right? So we learn through experience and also different kind of examples that we see on our real life. So we're going to apply the same concept to the machines where we give them a bunch of different examples. So for example, this is a very famous MNIST dataset, which consists of different kind of handwritten digits. So you can see that these are zero, but zero can be written in various forms depending on the different persons. And this is a 1, 2, 3, right? So we will pass these pictures, okay? This is considered one picture. of the zero, second picture of the zero, third picture of the zero. We'll pass all these pictures with the labeling, which is labeled that this picture is zero, to the machines. Okay, we'll pass all this information, the pictures and also the labeling, or we call it Y true, to the machines. So this is what we will need when we ask the machine to learn. We need a pair informations. Okay, pair information. The picture, which is the inputs, and then the outputs would be the corresponding Y true, which is the label, which is this picture and these pictures corresponding to zero. Okay, so we'll need this pair of informations and pass into the machines. And the whole idea of the machine, how it learns, is it's try to just doing optimizations where it try to minimize the loss, where the loss is calculated using a functions that computes the error between the Y predictions by the model and the ground truth or the Y true, which is the label. So when your prediction of the model and the true value is near to zero, it just means that your model are doing very well in recognizing all the handwritten digits. So the whole concept about AI in learning is try to minimize the loss between the prediction from the model and also the right Y true. And we call this technique as a supervised learning. Okay, so supervised learning over here is that you will have a labeled data where you have the inputs and every input has their labeling. So it actually discover patterns in the data that relates data attributes with a target class attribute. Okay, target class attribute over here refers to the Y true. So this is a supervised learning where you were given the labeling of each input. Something that's very important when we want to do deep learning is that we know that we pass in input and outputs to the model. So if we give an unclear input, logically, it will give us an unclear output as well. So it is important that we pass in a precise input, and hence the model is able to learn so that it can give us a precise output. And this is when you give unclear inputs and give you unclear output. This is what we call the common terms, which is GIGO, garbage in, garbage out. You pass in garbage into the model, it will give you rubbish predictions. Same goes when our human learn, right? So if we teach the students unclearly, and student may not be receiving the information well. So this is GIGO. So this is a machine learning pipeline. So this is a standard pipeline where we always need to design the experiment. After that, I need to identify what type of data we have to collect, and then move on to do data collections. After the data collections, we will need to clean and also pre-process the data. After cleaning the data, then we only do the training and tuning the model. And lastly, we'll evaluate how good is the model performance. And doing machine learnings, most of the time, data scientists or the researchers spends is actually on the cleaning and organizing data. So 60% of the time, we work on a deep learning model is really cleaning and organize the data. We want to ensure that the data that we pass into the model is clean, right? We don't want to have a very dirty data or noisy data, especially when your data set is not that a lot, you will end up with garbage in and garbage out. Okay, so it's very important that we spend the time on cleaning and organizing the data. And then next would be data collections. So we also spend time for data collection as well, especially when we do on healthcare stuff. We'll have to collect the data, and if we do supervised learning, so it's also taking a lot of time in doing data annotations. So you will see that's building training data sets, refining algorithm, and also mining data for patterns would not cost you a lot of times. The most time that we spend is on cleaning and collecting the data sets. So this is supervised learning. And there are also two other AI techniques as well, which are the unsupervised learning and also reinforcement learning. For unsupervised learning, the data will not have any target attributes, meaning that when you pass in the data, they won't have any labeling. And then reinforcement learning is a technique that it interact with the environment and then it decide on actions and learn by trial and error methods. This one is actually a reinforcement learning technique is actually applied for chess game. For example, when you're playing a chess, every step that you take, the environment will change. Okay, so based on the environments, we will need to decide what kind of actions so that we can win the game. So this is the reinforcement learning idea. So for supervised learning, we can also classify into regression and also classifications. For regressions, it will be predicting a continuous variables, right? For example, if you want to predict the temperatures, the exact continuous variable. For classification is predicting a categorical variable. It can be predicted as hot or cold, or we want to predict whether the person have cancer or do not have cancer. So this is classifications. So the whole idea for supervised learning is what we want to do is we are just learning a functions. Okay, we're just learning a functions that map between the input, the x, to a y, right? So we are learning a function that map between the x and y. So in these examples, we want to classify the 3 different type of flowers using the characteristic of the flower, the sepal length, sepal width, petal length, and petal width. So these are the x that we're going to pass it in, which is our x. And then we're going to map into the y, which is a Santosa, versicolor, and also Virginica. So the whole idea for supervised learning over here, we want to learn a function that map between x and y, and then we try to minimize the loss between the predictions and also the y true. Same goes for image classifications. So if you pass in an image, right, all of the image are represented by the pixel value. So for this is a RGB. So it's a color picture. So you have 3 channel, red, green, and blue channel, RGB. And all these channel will have indicated by the pixel value. So what does the computer see is just all this number. So all this number will act as an X, okay, which is the input, the X. And then what we try to learn is try to find functions that map between X into the Y. The Y would be the labeling, be it or cat, dog, hat, or mark. Okay, so the idea of supervised learning is really just finding a good functions that map between X and Y. Same goes for regression. So for regressions, instead of the categorical variables, we are actually mapped into the continuous variable, which is the price. If you have a 2D multivariate, so we will have a multivariate regressions. So that is for supervised learning. For unsupervised learning, we don't have any labeling. Okay, so the goal is we want to explore the data and then we want to find some intrinsic structures or similarity in them. So for example, if you're given this data sets, if you were asked to cluster them into 3 clusters, so we will base on their characteristics and group them together. So you can imagine it's like if we have a bunch of students and we want to classify into 2 groups. Okay, so maybe the characteristics that we can see perhaps is a male and female, then we can group them into 2 different groups. But we do not have the labeling. It's just purely based on the similarities of their characteristics, and then we group them into the same group. So for example, a group of similar size together to make small, medium, and large t-shirts. Okay, so tailor-made. So all this can be tailor-made for each person, but it's too expensive. So that's why we can group the different peoples into small, medium, and large based on their size. Or when we do in marketing, segment the customer according to their similarity, so that you can propose or plan some marketing strategies to target a specific users that match with their things. And lastly is the reinforcement learning, where it's try to learn with the environment. So in the reinforcement learning, actually you will have agents and also environments. The whole idea is actually if we based on the environment that we have, we depending what decide an actions, and then these agents will do the actions, and then the environments will change, right? Then after that, based on the current states, we'll give the rewards. Oops, sorry. Okay, based on that, we will give a rewards. So the whole idea of reinforcement learning is that when you can analog it to a chess game, okay, like a game or any games where when you make any move, the whole environment change, right? So based on the environment, then you decide what kind of action you want to take. And based on that actions, you will calculate the rewards. Okay, the reward is something that we have to decide or we calculate. We have to decide the functions that how do we want to characterize the rewards. So with that, it's a try and error method. And then from there, we will decide what kind of action to take so that we can maximize the rewards. So that is about some basic AI concepts. So we talk about supervised learning, unsupervised learning, and also reinforcement learning. But in health informatics, most of the research, majority of the research are focusing on supervised learning. Slowly, we are actually moving on to unsupervised because we are aware that there are too much resources need to be spent on supervised learning because we have to spend time in annotating the label, the pictures, right? Because we have to have a pair of informations when we do a supervised learning. So in the following slide, later on, I will be sharing with you some of the examples and also the applications that uses AI or machine learnings to solve a various different kind of medical problems. So these are some of the projects that my labs is working on. We are currently using AI to predict dengue severity, do some breast cancer cell analysis, and etc. I will share with you some of the work that we have done in the past, where we use various kind of AI techniques to solve various medical problems. So the one of my studies is really focusing on the small for gestational age, which focusing on small babies. Okay, small for gestational age babies are referring to babies that do not receive enough oxygen and nutrient during pregnancy, and hence they were very small inside the womb. But the current detection methods are the detection rate is quite low. So back in 2019, we started to think like, what if we can just use a machine learning and apply to see whether we can do better in predicting the SGA using the maternal information and also the fetal biometry measurements, which are the ultrasound measurements that we obtain from the ultrasound scans. So you can see from here, we compare with the different machine learning models, random forest, support vector machine, and also MLP, multi-layer perceptrons, and with the clinical diagnosis, right? So you can see that the sensitivity of all of the machine learning models are considerably higher than the clinical diagnosis, but the specificity is not. But in overall, the accuracy, MLP has the highest, which reach around 70% as compared to the clinical diagnosis. And from machine learning models, especially on random forest, you can also compute the importance score for the predictions to see which features has the most influence in the predictions, right? So as you can see from here, nuchal fold has the highest importance score. So this is quite surprising to us because nuchal fold is not related to SGA at all. Nuchal fold is being scanned, the purpose is to scan for Down syndrome. There is very little evidence to relate nuchal fold and SGA, while UT, uterine RI, resistance index, and uterine pulsatility index, which is the blood flow, are the ones that are important. But from here, we notice that it's not that these two features are important, but nuchal fold is more important in our SGA prediction in our study. So we dig deeper and see whether it is true or not. So we went back to a very basic statistical analysis where we just compare the features between the 3 different groups. Okay, so this is the birth weight above 10 centi, which is a normal baby. And then this is the small baby. This is an extremely small baby. And we confirm our findings that NF, you can see that for small babies, the nuchal fold is 4.36 and 4.29, which is extremely significantly smaller as compared to the normal baby. So it then hence give us the idea to even further to identify whether we can understand how does the model works, why is the model using NF to use it as a important features. Then we'll move on to the next steps where we want to try to understand how does the model make decisions. So this is something related to like explainable AI. We try to find ways to explain the model predictions. So for explainability or the interpretability methods, there are actually two different types. One is the global, one is a local. For global technique is actually the whole idea is we want to understand how does the trained model make predictions, which you can use it using ALE plots. While for the local, we want to understand why did the model make a certain predictions for an instance. Meaning, let's say if I have these patients and these patients, the model predict as SGA, okay, small babies. We want to understand why, what is the reasons, okay? So we can use the SHAP, SHAP, sharply addictive explanations technique to answer these questions. So as you can see from here, we did an ALE plot for the different features, uterine RI, uterine PI, and also abdominal circumference. And how do we understand this plot is that, so for uterine RI, if your RI is above 0.5, then the chance that you are born with a small baby or fetal growth restriction, FGR, is higher. If your RI is less than 0.5, then your chance of being born as a normal baby is higher. So we compare this cutoff value, okay, 0.5, 1.59, and also 167 with the clinical diagnosis guideline. And it shows that the error between the threshold value that we obtain from the models and the clinical guidelines are pretty small. So we'll move on to apply the same thing on the nuchal fold, where you can see that if the nuchal fold less than 3.7, the chances of the baby born as FGR increase exponentially, okay? But if the cutoff should be roughly 5.4, but the chances is plateau up to 3.7, then it's only increased up to exponentially. So we suspect that maybe the cutoff value can be in between 3.7 to 5.4 millimeter for nuchal fold. And also from here, using the SHAP analysis, we can also try to understand why is this baby being born as healthy newborn. So as you can see from here, the AC, which is the abdominal circumference, the tummy, which is very big. So that's why we think that the model think that the baby gonna born as a normal baby because your tummy is very big, which kind of makes sense and also match with our clinical knowledge or domain knowledge. For example, for FGR newborns, you can see that if the UTRI and UTPI have a very high importance score, so when this RI and PI is very high, that's why this instance or this baby is predicted as a FGR baby. So with this using this kind of method, we are able to understand the reason behind of why does the model make certain predictions, and also on certain individuals. So just now we validated that the nuchal fold cutoff value could be between 3.4 to 5.4 mm. So we move on to creating a nuchal fold growth chart, which act as a benchmark. So over here, you can see that this is the nuchal fold growth charts. We will use like a clinical guidelines where we compare with if we just use the EFW, which is the current clinical guidelines, and the nuchal fold. You can see that the sensitivity actually increases slightly, not that high, but 0.089 to 0.24 if we add in a nuchal fold, rather than if we use the only EFW, right? So EFW over here is estimated fetal weight, where current clinical guideline is using this fetal weight to judge whether the baby is small or not. And we propose that we should also look into the nuchal fold as well, okay? And we show that if we add in the nuchal fold, you can see that the sensitivity increases. specificity drop a bit, but overall the F1 score increases. And then we also apply a machine learning models, and we show that using the machine learning models, which is the logistic regression, give us the highest balance accuracy. The reason why we have to use balance accuracy is that because when our data distributions is imbalanced, accuracy is not a very good metrics for imbalanced data. So that's why we use balance accuracy. And we show that using using logistic regressions, we're able to achieve 70% of the predictions using logistic regression with all these factors. So those are some of the research that we did before delivery. So after delivery, we also try to use some deep learning model such as 1D CNN, LSTM, and hybrid model to predict heart rates, okay, neonatal heart rates, using the respiratory signals. So the whole idea is that when a neonatal is very fragile, right? We don't want to have too many wires to attach to the model, the babies. So what we hope to achieve is that are we able to do heart rate predictions from others signals as well? As you can see from here, using 1D CNN and LSTM, the MAE, the mean average error, achieved a 9.03 and 9.24. When we combine with both models, the MAE reduces to 9.008 with a RMSE of 10.68. And we show that when we combine models from different deep learning model, it's able to achieve better for the heart rate predictions. Another study that we also did is that this is a cell studies where our collaborators is interested in understanding the cell migrations. So what do they have is they have a cell where they culture and then they observe every 4, 8, 12, 18, 20, and 24 hours. In their conventional way, what they do is they label them and then they calculate manually. So it is very time consuming and also tedious. So we are working together with them to do an automated analysis, which means that we train a encoder and decoder model to do the segmentations. So what we have is we pass in the images in, and then we will have the segmentations of the cell. Based on the cell, we get the outline, okay, and then do some additional post-processing analysis like computing their radius, their areal, and then a single cell analysis. And we can see that using this, we are able to achieve faster analysis and enable to identify time-lapse migratory patterns for tumor spheroids above metric substrate interfaces. So using the segmentations or deep learning model with such a pipeline, we are able to automate stuff, and then we can enable researchers to spend lesser time on the tedious work. Another study that we work on is we try to use deep learning to predict the age of a person. The reason why we want to do this, the motivation why we want to do this is because it's lie on the sports and also the immigrations field. Especially when you are 18 years old or 21 years old, the actions mixed towards adults and also adolescents underage is totally different. So for example, I give a scenario is that for sports, we have to make sure that everyone report the real age, right? So in the sport area, what they do is sometimes they will just ask you to report your age, and then when they want to verify, we can make use of these methods. We can ask them to give an X-ray. Okay, from the X-ray, we are able to identify what is your age. So from here, you can see that we have a different kind of X-ray with different ages. And from here, we train a pre-trained CNN model and able to achieve a mean and median absolute error of 1.16 years and 0.957 years respectively. Okay, and then using also the GradCam, we can also identify the important regions that where does the models are looking at. next would be another work of ours where we use fetal head circumference estimations using deep learning techniques. So currently, when the sonographer are actually measuring the fetal head circumference, what they do is they capture and then they draw a circle on the head circumference, okay, and then they measure using the machines. So what we want to do is we want to try to reduce we want to make it automated system, right? When we capture and then we can let the AI model to direct measure the head circumference. Okay, so what we do is we just train a UNet, a very common UNet based model to get the outline of the head circumference. So as you can see, we use external data sets to train because it's very expensive if we want to use our own hospital data sets and then we want to annotate them. So what we do is they are actually open source data set HC18. We use that to train, and when we apply to our own hospital data set PPUM, it actually achieve kind of lesser dice score. Okay, so but it's still comparable, it's 70.48. So you can see from here we are actually able to use a simple UNet model, and then we just do a transfer learning, train on a HC18 dataset, and then pass to our PPUM. So the whole idea over here is we want to combine with our previous machine learning model as well. We'll get all the head circumference, we get the pictures, and then we get the measurements, and then using this measurement pass into another machine learning models, and then we can do a predictions of whether the baby is small or big. So those that I have just explained to you or shared with you are mostly on pictures, images, and also on tabular data, like the measurements directly obtained from the images. We also do some analysis on the SUSA report, which is a suspected unexpected serious adverse reactions report analysis framework, where some of the pharma company, they have research on new drugs and they want to do some clinical trials, right? And then when they do clinical trials, if there is any adverse outcome on the drugs, the personnel will have to write a report based on the drug reactions. And the reports are actually very lengthy. And if you written by different persons, the style of the sentence will be also different. So we want to come up with a way on how to automate the process. So over here, we will have these informations, and then we are trying to use LDA and also by LSTM to see whether these persons, when we give them the drugs, whether they are recovering or they have recovered or they are not recovered. Okay, so based on our very preliminary analysis, we're able to predict quite well with the sentences that is obtained from the report. So you can see from here that when the true labeling is recovering, the predicted label is also recovering, but the percentage, the confidence score is not that great. So currently we are still trying to find ways to increase the confidence score, but the whole idea of using deep learning and to analyze the SUSA report is kind of convincing. This is also another work that we are working on, which are just quite preliminary, where we want to understand or predict the long COVID predictions using knowledge graph and graph neural network integrations. So graph neural network is also just recently, maybe 5 or 10 years before, that's just being proposed, where you can, instead of using the structured CNN model, you model the whole architecture in a graph architecture, where you connect the different features with some connections, and then from there we can do predictions based on the graph neural network that we design. So the whole idea about graph neural network, the advantages is that sometimes it will be more understandable, because using CNN or the very deep learning model like LLM transformer, sometimes it's just like black box. We couldn't understand what's the reason behind. We can use the post hoc explainability method such as the SHARP and also the ALE, but the idea may not be that accurate. We still need some clinical expert to come in and see whether it's true. So graph neural network recently gained quite famous popularity because it is quite flexible, and because of the graph network architecture, we can able to embed the knowledge graph inside the network, and then we train, and it will allow some explainability reasons. So those are some of the research that we are doing. So the next thing I want to share with you all is after paper published, then what, right? So a lot of studies in the past have proved that AI is very accurate, is very convincing. But what we need to do now is we really want to bring the AI into the clinics, right? We want to apply in our real life. So people also start to raise out to we want to bridge the gap between the research and also the practice. But it is not easy to implement AI in clinics. There are a few hurdles that we have to solve before we pass into the clinics. First is on the algorithm robustness, the generalizable, fairness, bias, and explainability. Some study already show that when you train the model using the data set from one hospital and you apply to another hospital, the result drops significantly. For example, this is a very famous IBM Watson issue where the AI model developed by IBM to provide recommendation on cancer treatment did not perform well in poor and middle income regions. The reason could be because the data set they obtain or they gather may not be the same. That's why it fails. Same goes for this Fiona screening CNN model. And there's also another big issue in the machine learning based science where there's a data leakage problem and hence causing the result is not reproducible. And this study have already reported and summarized that you can see that among all of the papers that's reviewed, these are the papers that have pitfalls, okay? They have problems. For example, they don't have any test sets. The feature selections has based on train and testing. There are some duplicates. So there are different problems exist in the journal paper. And after they fix it, you can see that the reported result, okay, is like this. After they corrected the result, solve all the pitfalls, the predictions, the accuracy or the performance drops. Okay, you can see that majority the trend have a downward trend. So meaning that when we look through the journal papers, we have to identify whether the performance is believable or not. We have to look through their methodology, right? To ensure that whatever they do not have a data leakage problem in their studies. And that's why it's good that we have to follow the tripod guideline to identify all the informations over here so that when the paper that is published, when we read, we are able to judge whether it's comparable to ours, whether it's correct or not. So these are some others challenges, like for example, data governance, stakeholder consensus, legal compliance, and also ethics and moral code of conduct. But I think different organizations are making efforts to try to make AI software as a medical device. So as you can see from here, FDA has actually come out with a plan for the AI software as well. So the takeaway message for my this talk is AI can help in many ways, but we have to think hard during the problem formulations. Is it whatever, do we really need AI to do a certain task, right? For example, if there is already existing technique that are performing very well, why do we still need AI? Is it AI will bring us better benefits, shorter times, or automated way? And lastly, publishing is not the end goal, but translating the whole AI model to practice is. And together we transform and improve health using AI and engineering. I think that's all from my talk, and I would then acknowledge the students and also the collaborators and the grants for supporting all the research. Thank you very much.
Okay, thank you for your great presentation. Your presentation gave us the the series and the application, and also include the expectation for the future research and clinical applications. Yes, thank you very much. And I think there is a question from Dr. Arimura, and the question is, what data augmentation method did you use for unbalanced data? Yeah.
Okay, thanks. So for data augmentations for images, we use okay, let's say I'll just give examples on one of the studies. Let's say let me go back. Oh, I think it's hang. Okay, never mind. So I'll just share with you all one of the studies that we use the X-ray to estimate the age, right? So the augmentation that we use, we are just using flipping and then flipping left and right, and also changing the contrast, changing the image colors. We do not want to do too much of the augmentation. The whole idea is to try to augment it such that it's does not have, like, if you rotate 90-degree, it doesn't make sense. What we do is we try to augment such that the data set that after we augment is still kind of makes sense. So the answer to that is like flipping, rotations, color, change the contrast, all these kind of data augmentations. Yeah.
Okay, thank you very much. But I'm talking about image features. Not
the features?
deep learning research.
Oh, for the measurements.
Yeah. If you have unbalanced data for
Yes.
using image features with machine learning, so you need increase the number of data.
Yeah. So for the features that you for the features we use oversampling. Oversampling is just oversampling we just duplicates the minority data set.
Okay. We use smart technique, but we have sometimes we have better result, but sometimes we don't have.
Yeah,
So,
because I think the smooth is because it's based on the distribution of the data set, and then you try to generate a new data set based on that distributions. So if your own data set, you do not have a lot of data sets and your distribution is very wide, so somehow you may have the data set that you created from smooth may not be realistic, sir.
Okay, thank you very much.
Yeah.
Okay.
Okay, thank you. Any other questions?
Can I ask more?
Yes, please.
Okay. So I think you mentioned about the data leakage problem.
Yeah.
Yeah, that is I think a big problem. Sometimes my student did that that problem, so I noticed the problem, and I think many papers already published. No, many research already published with this data leakage problem. So, but how do we check?
Check, right? Okay, normally what I ask my student do is that they have to go and look through their methods, see whether they report. Are we able to know that let's say do they oversample? Because if you oversample and then you split, that maybe have a data leakage issue.
Yeah.
Yeah. So read through the method. If they don't report everything, I ask them to like you believe like you should not believe 100% lah, because we can't judge 100%, right? So take it as a pinch of salt for the result.
Okay, thank you. Okay, thank you.
Okay, thank you. And Dr. Li Shao, if you don't mind, shall we move on to the
Sure.
third presentation?
All right.
Yeah,
Thank
thank
you.
you. Thank you. And it's my pleasure to introduce the Dr. Mazen Soufi. He came from Nala Institute of Science and Technology. And the topic he will give is the basics of advanced AR architectures and applications to musculoskeletal analysis. Yes, please, Dr. Mazen Soufi.
Okay, thank you very much, Professor, for the kind introduction. Can you see my slides?
Yes, very good.
Okay, thank you very much. So, hello everyone. This is Mazen Soufi from Nara Institute of Science and Technology, Imaging-Based Computational Biomedicine Lab in Japan. It's a great pleasure for me to be with you today. And my presentation title is Basics of Advanced AI Architectures and Applications to Musculoskeletal Analysis. First of all, let me first introduce myself. I obtained my bachelor in biomedical engineering from Damascus University in Syria. And thanks to the Japanese government scholarship, I could obtain my master's and PhD studies from Kyushu University in 2014 and 17. And currently I work at Nara Institute of Science and Technology as an assistant professor in the Imaging-Based Computational Biomedicine Lab. So as you know, Nara, for those who don't know about it, it's a city that's located at the center of Japan, and it's famous for its very unique culture and very beautiful temples, and especially the beautiful deers that are very beautiful and respectful, as you can see in this image. They will bow to you if you give them some snack or greet them. So I highly recommend everyone to visit us in Nara. And our institute, the NICE, is famous for being the host of the research by Professor Shinya Yamanaka, who was awarded the Nobel Prize in Physiology in 2012 for his research on the iPS cells. So my research interests are working on deep learning, musculoskeletal image analysis, and disease progression modeling from images. Actually, I'd like to take the opportunity to do some of our motivations for working on the musculoskeletal analysis. So in our lab, we mainly work on topics related to musculoskeletal analysis. One of the motivations is that the current standard tools for analysis of the human motion, such as what's called the OpenSim simulation tool I'm showing here for rehabilitation and sports medicine, it depends on templates that are scaled to fit the size of the target patients or subjects. So several studies have pointed out that this kind of fitting approach does not consider the geometrical properties of the musculoskeletal structures of each patient. So indeed, if you look at the right-hand image I'm showing here, which shows the muscles of 4 different subjects we obtained from CT images, you can observe that the variations in the muscles, such as the blue one I'm showing here with the arrows, are different from one patient to another. Therefore, we are highly motivated to make the human motion analysis more patient-specific by involving the medical images into the simulation softwares. And the second motivation for our work on the musculoskeletal analysis is that current tools for the analysis of several musculoskeletal diseases, such as sarcopenia, which is known as the muscle atrophy or the fatty degeneration caused by several factors, does not reflect the current tools that does not reflect the actual situation of many muscles or patients, because they are mainly working on 2D slices, such as the one I'm showing here, or the recently developed tools such as the total segmentator, which is a very useful tool. However, it only addresses some of the partial structures in the musculoskeletal system. Another point is that disease widely known for aging societies, which is osteoporosis, which is known as the degradation of the density of the bones in the patients, is also currently depends on using specific modalities such as DEXA images. So these techniques are not usually available for many regions due to several reasons. So we are aiming at finding more straightforward, easily accessible tools that are needed for the diagnosis. And our third motivation is the analysis of musculoskeletal disease progression in large-scale databases. So in Japan, the JMID database, and I believe in many other places in the world, but mainly in our research, we are addressing the database in Japan, JMID. This database is collecting hundreds of thousands of medical images from multiple centers across the country. So we are particularly interested in exploring the relationships between the musculoskeletal structures and the demographic information in the population, such as the age, the sex, or the disease status, etc. So next, let me introduce our lab. So our lab is directed by Professor Yoshinobu Sato and Associate Professor Yoshida Otake, who have long research experience on the musculoskeletal image analysis and development of image or computer-aided surgery techniques. So our research interests covered several topics, including muscle segmentation from MR or CT images, X-ray fluoroscopy for the analysis of the 4D foot measurements, the estimation of the bone mineral density from conventional X-ray imaging, and the muscle and bone decomposition from X-ray images. So we are finally aiming at leveraging computer vision and machine learning approaches for diagnosis, treatment, and understanding of the musculoskeletal system. So here comes the contents of my talk today. First, the first part, I will introduce some of the basic of advanced AI architectures. Dr. So has excitingly introduced many of the interesting topics in AI with an overview of the overall artificial intelligence topic and its applications. I will go a little bit deeper into the details of some of those structures, and then I will explain how we are applying some of those techniques in our musculoskeletal analysis research. So first, sorry if this has a little bit repeat, but I will give it from a different view, if we can say. I will start with some of the topics that are essential for understanding machine learning or deep learning in a special case. So I have believed that many of you have already familiar or experienced with these tools, but let me start with supervised learning. So the main concept is that in supervised learning, which has special importance in our field as the medical knowledge is really guiding a lot of our applications, is that if we have assuming that we have two images, one having a label malignant and the other having a label benign, we want to extract features that I'm showing here as X that finally help us to build a classifier that can automatically predict either of these output labels from the input images. So the basic question is, how can we derive the features that give the highest accuracy in the output prediction? And the contrary, the unsupervised learning is the second type that I would like to explain, and it entails algorithms that help to compress or summarize or compactly represent the information in the images. So the basic technique is to develop a model that encodes and then decodes the compressed information to reconstruct the input images. So this would further help in the analysis of large images in a compact way and help us understand the underlying patterns of variations, for example, between controls or disease cases, or further between subtypes of the same disease. So the question here is how to derive the features that compactly represent or summarize the data that are giving in the input. And the third type, which has recently witnessed a remarkable progress in the era of deep learning, is generative modeling. So this family of models builds on the concepts of supervised and unsupervised learning to come up with models that can generate synthetic, diverse, and meaningful samples that maintain specific features, but decoded from totally random vectors. So these models are especially useful in generating synthetic images to extend the training data when we have a scarcity in these data sets. So one example of these models is the latent diffusion model, which I'll explain a bit later in detail. But again, to emphasize, the question here is how to generate and synthesize data samples that hold the specific features. So again, maybe you have noticed that I'm repeating one word repeatedly in the 3 slides, which is the word here, it's features. So how to extract the features is the main task. And I show here the 3 main approaches that build basic blocks of large stream of applications in our field. The first is the human-crafted approach, where mathematical models, such as statistical, geometric, or texture ones, are built based on our abstraction of the relationship between the outcomes and the appearance in the image. So Professor Arimura has extensively explained about this topic. In my talk, I will focus on the two types. First, the convolution ones. So here I termed this convolution. It's very famous to be called just convolutions, but I would like to emphasize the word learnable convolutions here. So the intuition behind the convolutions is how to automatically extract the visual features that present the data. So assuming that you have a fixed kernel, I think many of you are already familiar with these kernels because it's widely used in image or simple image processing tasks. We design the weights of this image and convolve it with the input image in order to produce an image that has a specific feature. For example, here I'm using a Sobel kernel to produce an edge-enhanced image. However, it's very hard to design these kernels. So taking an example, the features that are present in images of lung cancer, you can see here that there's many types of features that can be hardly designed to be implemented using such simple or small kernel. So we need many filters, we would need many variations, a lot of trial and error to reach the most suitable kernels to get these output features. However, the idea behind the learnable convolution is that we set these parameters to be learnable. That means these are just variables. And these variables will be learned, optimized iteratively by giving it the input image and the output image. Say it's an edge enhancement image here, or give it like a disease or some cancer subtype. Whatever it is, the model will try to learn what are the best ways to produce the features in the image. So this has helped to build large convolutional neural networks from these small concatenated filters. And given that the idea that these features or visual features can be present in the same image at different locations, for example, here, you have the same feature appearance, but it can be enhanced with a single kernel. So given this fact, the same kernels can be used or shared among the image, and that's why it's called weight sharing. And these filters can be concatenated in a hierarchical way to give more representative features at different scales. So this has ended up with very nice and practical way to analyze the images. And actually, since 2012, we have witnessed that these filters can really represent very complicated features that cannot be designed manually using conventional techniques. And some of the applications are the unit model architecture. And this model has witnessed wide applications in the segmentation field because it's constructed of a simple architecture from a contracting path and an expanding path that downsample and learn to downsample and upsample the features, and then concatenate the features using the skip connections from the downsampling path to the upsampling path to compensate for any missing details that were missed in the downsampling process. So this model with its variation, the NN unit model that is a self-configuring version of it, has witnessed wide applications, which are really one successful example of convolutional neural networks. And the second type of how to extract the features is what I call a learnable attention. So usually it's called attention, but again, I emphasize the word learnable here to indicate how it's working. So the intuition behind the attention is that how to automatically weight the importance of specific parts of the data in relation to the others. So instead of putting a kernel and making relationship or assumption between each voxel and the neighboring voxels, we give the data or give the model the capability to learn from the data the importance of the neighboring voxels or patches automatically. So by the attention, it's actually another word for saying projection, because it's basically computes product between the vectors. So assuming that you have two vectors, if you have the vectors are very similar to each other, you will have a very large dot product output. And if you have two different or dissimilar, unsimilar vectors, the projection will be smaller. So building on this, if you consider these vectors as patches, instead of assuming a fixed dot product operation, we try to learn this dot product. In other words, we try to wait out how these projections are obtained by learning from the data. So this process is made by concatenating the patches into arrays called embedding arrays. So each row is one patch and each column is one dimension of these representations, and giving them weight arrays for query, key, and values. And these weight arrays will be learnable during the process of calculating the attention. So if your target variable is you have a specific output and desired, all the model will try to learn this attention score, how to maximize the attention scores giving your target output. So again, in summary, it's just a weighting of the dot product operation, but in a learnable way. And this has started with the transformers, which was used for the machine translation application. And these figures, if you look at the paper, you will see this figure. It's the same as which I was explaining a little bit earlier, but with some specifications for the language process, as this was a translation paper or machine translation paper. And the innovation here was that making this kind of heavy calculations and optimizations possible using a parallelizable attention computation using the multi-head attention. So this was the language version of the model, and the vision version was the vision transformer model, which was developed in 2021 and has already witnessed high adoptability. So the third model was the stable, the generative models. I'd like here to showcase one of the recent models that are gaining wide popularity and was introduced by Dr. So. So these diffusion models are actually used for synthesis of artistic works such as the DALL-E API or the other Midjourney tool. So these models receive some of the prompt text from the user, and they can produce very nice artistic figures. In the medical image analysis field, they have also witnessed some applications, including producing synthetic images for cancer subtypes, such as in this recent paper in 2023. So first, what is the diffusion process? The diffusion, is its physical meaning is that starting from an initial state of the material or the system, the model progressively changes its state from one time step to another until reaching a final state. So here I'm showing this animation that I have made by an ink and a cup of water, that giving from a single or a few drops of the ink, you can see how the water particles are getting diffused with the ink particles. So this process continues gradually. I will not show here the whole movie, but it ends after, for example, 500 seconds in a totally diffused ink. So the assumption behind the diffusion models are, is it possible to start from one point in the final state and return to the initial state? So is it possible for any computational process to collect out these small steps that the ink has diffused in the water until we can reach to the clean state and the condensed ink in the one spot? So going through this operation, the assumption is that we can decompose this whole diffusion process into small steps, and each step is just an addition of a little bit of noise, and repeat that repeatedly until we receive the final state. So if you consider this from 0 to 1 in one step, this is impossible. But if you go this process in an inverse way with very small time steps, this might be possible. So again, in the case of the stable diffusion model, the assumption is, sorry, here, this is a common diffusion model or denoising diffusion model. It's not the special case of the stable, but anyways, the main process is that we have a noising, or you can consider this as putting an ink and making it diffusing all over the water, reaching this noisy image. And the denoising process is starting from this very noisy input and reaching to this clean input. So the assumption behind the stable diffusion models, or diffusion models in general, is that if the model can learn how to generate an image like this by denoising it in small steps, it will hold the capability to generate a good example from any noisy sample. So this process, starting from the noisy image, reaching the clean image, is what is called the denoising process. And this is the learnable process in the stable diffusion models. So doing this process, actually, we think about it, we look at the image and we think this is easy, but actually this can be done in 100 or 1,000 time steps. And this is done on each pixel. So if you consider an image with 320 by 320, doing this process for 1,000 times, this is very computationally expensive. And this is done by usually by convolutional models. So doing the convolution inference for 1,000 times, you can imagine how much time it would take. So instead of working on the images in the original space, the idea behind the stable diffusion models is to work on the latent space. In other words, we use, again, unsupervised learning to compress the input image into a smaller representation, which I show here as a vector Z, and do the noising process, adding the noise, reaching the totally diffused case, and doing the reverse process or the denoising process using a neural network that is, in this example, it has a unit architecture to give it back to the original state. So all the latent space is just a compressed version of the representation of the original images. So that would reduce the computation time because you are not working anymore on the original image sizes. You are working on compressed representation of the images. All is done in the latent space. So even if it's done multiple times, 1,000 times, it would be less computationally expensive than doing this whole process in the original image space. In addition, it had other functions such as conditioning mechanisms that can help us not only generate the image, but also put some conditions like text. You can put some sentence, or you can put some images that would guide this regeneration process to reach your final output image. So I will go to some details of this model. First, it has an autoencoder that works in the pixel space. This autoencoder is just an unsupervised learning method. It takes an image and it tries to learn how to reconstruct the input image from this encoded representation. And the second part is the latent space that applies the noise to the compressed representation of the image, and it tries to denoise it using a unit architecture. So this process is done for many times, time steps. It can be 25, 50 until 1,000. And the third part is the conditioning that guides how to generate the images using some conditions such as I said, words or other parameters. So see, these stable diffusion models actually have witnessed a lot of popularity due to the highly artistic works that are done using text images and very good sampling, even though it has very highly computational process, but it's gradually getting more and more adoption because of its high quality samples. And another task was the image to image. I'm actually just getting these samples from their GitHub, from the author's GitHub page, and showing examples for image to image synthesis. You just try some simple images and it will regenerate this into a very artistic figure like this. And in the medical field, actually, it's also gaining popularity, starting from many applications, including image-to-image translation, reconstruction, registration, etc. So you can take a look at this nice survey paper published in a medical image analysis journal recently to gain a more deeper understanding of how many applications it's now covering. So as a summary of part one, learnable convolutional layers and attention mechanisms lie at the center of advanced AI model architectures. And stable diffusion is an advanced model for image synthesis that enjoys good sampling quality, but requires long training and inference time. So here comes the second part of my talk, our researchers on applications in musculoskeletal analysis. So I will show 3 examples of our work. In the first example, this is a work by one of our second-year master course students, Mr. Masuda. This paper is currently under review by IGCARS, and there you can find the preprint on this link. So this paper deals with hip osteoarthritis. For those who, let me just briefly explain what this disease is. Hip osteoarthritis is actually, and also knee osteoarthritis, is actually increasing in in aging societies. And the symptoms of this disease is that the distance between the femur, this is the femur bone, and this is the pelvis bone. The distance between the femur and the pelvis gets smaller and smaller as the disease advances. So for the normal hip, this is the normal distance. You can find it in this X-ray image. But for a dysplastic hip, this distance gets very small, and it's accompanied by higher density in the X-ray images. So the unaffected side looks like this, and the affected side has a lot of osteophytes, and it's accompanied by much pain and less mobility for the patient, and this would degrade his quality or her quality of life. So the background of this research was that we want to automatically grade the hip OA from the medical images. And actually, there are two main types that are used for of grades that are used for grading this disease. One is called KL grade, and this characterizes how much the distance between the femoral head and the pelvis is. So the smaller the distance is, the higher the grade will be. And the other is called CROW, which characterizes how much the femur head or the femoral bone has migrated from its location in the pelvis to the upper parts. So you can see here, for example, in a scale from 1 to 7, by combining these two scales into a severity scale from normal to severe, you can see that CROW1, KL1 has almost normal hip, but as the disease the severity increases, higher density will be noticed around the femoral, at the pelvic and the femoral articulation part. And gradually this will increase, reaching higher CROW levels. At the higher CROW levels, the bone will be displaced from its location. So you can see here in the highest severity case, all the femur has moved from its place. So that means a total dismobility for the patient, and this would require a surgery. So the related work so far, other studies have also addressed this problem. However, they are mainly focusing on binary classification. So whether the patient has OA or no hip or no OA. So in the case of no OA, this is a kind of normal case. And in case of OA, okay, this will tell from the automatic grading system that this patient has OA. So corresponding with our grading scale, this corresponds with around CRO1 and KL1. And all OA have the upper scale, the upper levels in our scale. So these studies have, for example, this in 2021 was validated on 94 cases, and it obtained an 83.3% of accuracy. Another study in +1 2017 was also validated on 420 cases and could obtain 90% accuracy. However, we still, if we use the binary classification, we don't know which level are we in within these severity scales. So what Masuda-kun has done was he did a study on a CT database collected from Osaka University Hospital, and it's contained internal training and testing data set consisting of 197 patients and an external testing data set including only 52 patients. And this shows the distribution of the grades in his data set. And the way we have done that is that instead of working on X-ray images, we're actually working on CT images. So starting from the CT image, we obtain DRR or digitally reconstructed radiographs accompanied with the KL and CRO grades. And here I show the overall scheme of his work. Starting from the CT image, we automatically allocate the femoral head part, crop the image, and apply an AP projection to obtain the DRR image, and use this image as input for deep learning classification model or regression to obtain the final grade. So in his paper, he's tried both system, the classification-based and the regression-based, using 3 different architectures, including the VIT model that I have earlier introduced. And looking at the results of his work, looking at the exact accuracy, which means that if you are inputting, if your ground truth is a specific level or grade, how much accurate can you get the exact grade among all the severity levels? And that was his accuracy was 0.656. in the case of the exact accuracy. However, if you give a tolerance, for example, if you get a grade of 4 and you accept it to be grade of 3, if the output model was grade of 3 or grade of 5, we call this as a one neighbor class accuracy. In that case, he would obtain an accuracy of 0.962, which is considered relatively high for application in large-scale databases. So looking at these, some of those qualitative results, we output the activation maps from the VIT model and project them in a lower dimensionality space using the UMAP technique. So using this projection, you can see how the distribution of the grades is taking with respect to the image features. And you can see here that darker points or darker images correspond with lower grades. And as you go to the green and yellow ones, you will see that this is have higher severity grades. So in some sense, the model is learning the severity levels from the images, looking just at this low dimensionality projection. For example, if you look at the some of the images, for example, this dark one, you will see that the ground truth class was 1 and the predicted class would be 1. However, for the class for an image that has higher, for example, take this one, the model has shown a prediction of severity class 4, or severity class number 2, but the ground truth was actually class number 4. So again, when we have discussed with the medical doctor who was working on the annotation, he said that it's more probable that the model's diagnosis was closer to the situation because it's actually should be closer to the class number 2 rather than class number 4. So the model, in some sense, is learning more representative features that more related to the disease than can be perceived by the human eye. And for the application of AI in musculoskeletal analysis, the second topic is the segmentation part. So we are working on muscle segmentation, including 19 muscles in the hip to the thigh, to the knee region. And in our daily life, we actually use these muscles, but without looking in detail which muscle we are now using to stand, to walk, to stop. And looking at the details of these muscles, you will really appreciate how much each muscle is doing an effort for us to move in a very smooth way. So take an example, for example, this blue muscle, it's called the psoas major muscle. So this muscle helps us in the flexion of our hip. The other muscle, the green one here, it's a small one, it's called the gluteus medius one, but it helps us in doing the abduction and achieving a balance during standing. The yellow big one is called the gluteus maximus muscle. So this helps us do the extension motion. So when you are from bending to the extended position, this muscle helps us to do that movement in a very smooth way. And it's the largest one in among these muscles. So these muscles are really important for our standing, motion, walking, etc. However, in hip OA patients, if you look at the CT images of these patients, you will see that it's not only the bone that it's getting diseased, but also the muscle, due to the loss of use, is also getting affected. So looking at, for example, the low severity cases, normal, you can see that there's high symmetry between the two sides of the muscles. However, when we go to higher severity levels, you can see that the left hand or the left side muscle is getting very smaller compared with the right side muscle. So this is called muscle degeneration or fatty degeneration or muscle atrophy, which means that decreased volume and the quality of the muscle with increased disease or other factor levels. So if you take these muscles out from the human bodies and look at them, the small muscle, which has very low intensity, is almost having very high fat ratios, while the muscle, which is very healthy, it has very high content of muscle cells. So this increased quantity of the fat ratio is very harmful for the muscle functions. And actually, many studies have been working on this and characterizing the composition of the muscles from the CT images. Taking an example, this study in 2014, it gave a scale on the CT values for fat, composite, and muscle regions. So using this information from CT images, it can help us know what is the health or what is the status of the muscle just by analyzing its issue values within the CT image. And other studies actually have worked on muscle analysis. For example, this study in 2020, it was applied on the UK Biobank. The UK Biobank database is very large, including, they are aiming at 500,000 patients to be imaged with MRI. And this study actually has shown relationships between the muscle volume and age, sex, and other factors. So it was a really interesting study, but at the same time, it's applied on MRI that has it was very rigid protocol that all the patients, or not the patients, the volunteers were imaged. However, in the case of CT, it's more like there's more heterogeneity between the scanners. There's more differences between the diseases, how the muscle looks like between a normal and the patient is so different. And so far, all the studies were done in 2D because it's very hard to annotate the muscles in 3D, as I will show later. So doing the 3D analysis actually is possible in MRI, but doing it in CT would be a little bit more, it's harder. So recently, some 3D-based approaches have been applied. One of these approaches have tackled the rotator cuff muscles, which are in the shoulder. But again, it's only targeting a few muscles. But we have a lot of muscles in our body. For example, in the hip to the thigh, we have around 19 muscles. So if we want to segment this from CT image manually, you can see, for example, in this small area that there are 3 muscles that are located next to each other. But looking at the borders between them is very tough. And doing this in, for example, 500 slices would be a really big pain. So doing this automatically would really be a very beneficial step for larger analysis and adoption in this muscle analysis in CT images. One of the techniques was developed also in our laboratory by Dr. Hiyasa. So this method segments the target muscles and also outputs uncertainty measure for how much the model is confident about the segmentation accuracy. So looking at the accuracy of this model, it was based on the Bayesian unit architecture. It was 0.891 of dice. However, so we are almost approaching 90%, but this study was only validated on 20 cases and not applied for muscle assessment in larger databases. So my work here was to use the Bayesian model to do this muscle segmentation and apply a qualitative assessment and quantitative assessment of how much can we get accurate estimation of the average CT values and the muscle volumes from the CT segmentations. Sorry. So this study was done on 50 cases, and I was using the 5-fold cross-validation to validate the model, and I was targeting also the 19 muscles that were addressed before. And we can see from these dice plots of each muscle that the auto-segmentations have exceeded 0.923 on average on dice. And ASD, which is a measure of how much error you have on the surface, has also a value of around 0.774, which is very low or less than 1 millimeter and approaching the voxel size in the image, which is really a good accuracy in terms of whether we can use these models for further analysis steps or not. And looking at how much accurate can we retrieve the volume and the mean CT value from these segmentations, we can see that for the 3 muscles, we are approaching very high correlations. And for the 19 muscles, all the correlations were larger or equal to 0.95. So we're only not targeting CT images. We have also trying to apply the automatic segmentation on MRI images, and also not only to the hip region, but also trying to integrate models from different locations. So taken, for example, in the MRI and CT, in the MRI study here done and recently published in IJCARS by the PhD student, Mr. Lee. He was trying to work on to develop a way to improve our active learning approach. Active learning means starting from a small number of data, training your model, and gradually increasing the accuracy of the model by extending the training data. So doing this step gradually and repeatedly for multiple times would reach larger annotated data sets with higher accuracy. But the question in his work was how to select the cases for each iteration. So you don't want to select cases that are very similar. Otherwise, you are not giving the model any new information. So his work was to use the Bayesian unit model and active learning based on the uncertainty to improve the way we are selecting the cases. And his idea was to involve a density module and a diversity module. So this density means you want to in some sense, you want to improve the similarity between. So first of all, you want to use uncertainty metric to select the cases, and then you want these cases to be as representative as possible for all your data sets. So he was using a kind of similarity metric. First, he wants to decrease the similarity with the labeled or training data set and have a lower similarity or more representative or diversity from the unlabeled data set. And by using his method, he could, so here he's showing multiple Bayesian learning or active learning approaches using different metrics for the selection. And by involving this kind of diversity and the similarity metrics, in addition to the uncertainty, you could achieve an accuracy, for example, in the case of the MRI image segmentation, you can achieve an accuracy of 85 or 91% if you are selecting slices. And you can reach, for the CT case, an accuracy of around 88% if you are selecting based on the CT slices. And that can be also noticed to improve not only the accuracy, but also reduce the time that if you are having an annotator, a medical doctor that needs to annotate these images, this would improve how much cost you are paying on this process. Another application was the integration of multiple models. So we're having multiple CT data sets, one for the hip, one for the lower than the knee, and one includes only the bones, other includes only the muscles. So how to integrate these regions or outputs of the models in an efficient way? This work is done by Mr. Masaki, a PhD student in our lab, and he was trying to use DRR images for integrating, for first using a YOLO model to predict where is the hip, where is the knee, and give each region its specific model, and then integrate these unit outputs into a single or integrated level. And this approach actually compared with other approaches that use slice-wise prediction of the anatomical location. This approach of using YOLO has shown better performance in terms of accuracy, and it would also reduce the step for doing the prediction of the location of each slice in the CT volume. And the final application is in our work is the decomposition of the X-ray images into muscle and bone images. So I think everyone knows about the conventional modalities we use for screening or health checkups is the X-ray images. Actually, these images are used widely for different applications, and it's actually exist in many locations in the world and the clinics, and they give us a 2D projections of the body on these 2D planes. However, only from these 2D planes, we cannot know where is the muscle and where is each muscle compared with its other location of the other muscles. So the purpose of this work by Mr. Gu, PhD student in our lab, is decompose this X-ray image into its constituent muscles and structures. So his work builds on the CT information in the training phase in order to learn how to decompose an X-ray image into its constituent parts. So you can see here, for example, for these two X-ray images, these two images after decomposition, they show different structure of the muscles. This big muscle is the yellow one, and this iliacus muscle have totally different appearance between this patient and this patient. So how to obtain this information? Actually, his work is a highly complicated work in terms of how many loss functions are used. However, this process in the inference time gets this complicated loss function gives us very much benefits in the inference time, because the model can learn how to decompose each structure from the image using a single run of the inference. So looking at conventional methods for estimation of the volume or the density of the muscles from the images, you can see here that the automated way can help us obtain the lean muscle mass in a very high correlation compared with the conventional way. So current correlation is around 0.87. And for the muscle volume, also we could obtain a large PCC of 0.9, which is really a high correlation in terms of relationship between the predicted and the ground truth measurements from CT images. So you can imagine the application of this, giving an input, one X-ray image, and you can get a detailed information on the decomposition of each of the muscles that are located within this X-ray image. So again, this is, let me skip, I'm already exceeding the time, but you can look more at the details of his paper published in MICCAI 2023 to see that very high accuracy from the models can be obtained. So as conclusions, we are actually realizing that deep learning tools are very helpful for musculoskeletal disease grading, segmentation from different medical images, and understanding of the disease progression. And these generative models could show potential for decomposing X-ray images into constituent muscle and bone. And several applications are being developed now, targeting multiple ROIs and analysis of large databases. So our work actually has been a fruit of a large collaboration from our engineering, data science students, and our clinical collaborators that are very helping us very much with the input, the feedback on the direction of the research, and of course the availability of the data that we are using in our work. So thank you very much. Sorry again for exceeding the time, and I would be glad if there's any question. And please, if you want to know more about our work, I'll be glad if you search for ICB Lab NICE or connect with me directly on LinkedIn. Thank you very much.
Okay, thank you, Dr. Soufi, and it's really a good presentation. And yes, it's your presentation will bring many benefits for the patients. And is there any questions?
Doctor, can I ask Dr. Soufi directly?
Yes, please.
Okay. Dr. Soufi, I have a question about CT value of muscle. Did you consider partial volume effect?
Yes, thank you very much. Since you are experienced in CT images, so I was a little bit afraid of your questions. So partial, actually, we are dealing with small, very small voxel sizes that are around 0.68 to around 1 millimeter. So these voxels have very so much information that it's not, the partial volume effect is not clear on those images we are working on. But from the analysis point of view, we did not look at how much this partial volume effect is affecting our analysis values. So if you would, if you would suggest for
no,
yes.
I don't have any suggestion, but some research have performed prediction of CT value within a voxel depending on tissues. For example, in your case, I think muscle and fat. You can classify the tissue CT value of tissue within voxel into two tissues. Yeah, kind of decomposition of CT value. Anyway,
yeah, interesting. Thank you very much. I will search for that work. Thank you.
Okay, and another question is regarding active learning.
Mhm.
So in this active learning, you don't have to prepare the many training cases with the labels, right?
Yes, actually, that's the final purpose, is that we need to reduce the time, the annotation time, as much as possible by creating small training data sets, but in the same time holds a lot of diverse information that can represent the population data set, if you can say. Yes, so that's the main point. Yes.
Very interesting. Thank you.
Yeah, thank you very much. And one thing I didn't mention clearly here, but Arimura Sensei was my supervisor in the master and PhD course. So thank you very much, Arimura Sensei.
No. Yeah, welcome. Okay, thank you.
Welcome. Thank you.
Yeah, back to Professor Zhu.
Yeah, thank you. I have a question to Dr. Soufi. Your model can predict the structures of the muscles, and have you ever tried your model to predict the muscles for the pediatric patients? I know maybe because you know that for some pediatric cancer patients, we care about the structures, especially for the growth point of the on the point of the bones, because that will affect to their futures. I mean, long side effects. So, have you ever tried that for the child?
Yeah, thank you very much. This is a very, very important question. Actually, one of my future interests is to look more into the muscle structure in cancer patients. So until now, we are mainly targeting HIP-OA patients in our data sets that are mainly aged, and they have the databases mainly contain different age spans from the pediatrics. So unfortunately, we did not try on pediatric CT images yet, but what I can say is that our model does, in this stage, I'm not expecting it to be very highly, let's say, accurate as much as the aged patients that we have, but I believe that the reproducibility of the HU of the measurements would help us look more into how much the cancer or how much the treatment also is affecting the health of the muscles. So I consider this a very nice question, because it would motivate me more to work on pediatric data sets as well. So in summary, we did not work on this, and I'd like to work on this in the future.
Okay, thank you. And at the beginning of our conference, there is a question about will the presentations, the slides will be shared, and I just think that maybe the video for this webinar will be shared on the official website. Yeah. Okay.
Yes, I agree. Thank you very much.
Thank you. So
okay, thank you.
Yeah, if there's no more questions, I think maybe it's time for the conclusion from Professor Jian. And I also want to show my appreciation to Professor Jian. And today is the first day of Chinese New Year, the Dragon Year. I wish all of you have a rising up achievement in the new year at the Fly Dragon. Okay, thank you.
Happy New Year to everyone.
Yeah.
Thank you.
Professor
Thank you
Jian,
for
please.
Thank you very much.
Yeah.
Can you hear me? Yeah.
Yeah, good.
Thank you. Thank you for the wonderful work from the moderator and our three speakers. As Professor Zhu just mentioned, actually this is the first day of Chinese Lunar New Year. And thank you for hard working on your first day, actually doing this wonderful moderation for our iPhone. The iPhone, the recorded video for this webinar will be shared on our iPhone webinar. Actually, our chair or our science committee, Mary, And John from India had just posted a Facebook feedback link from the in the Google, so you can see the chat box. It will be shared. Also, actually, at the beginning, I forgot to introduce our moderator, Professor Jian. He's actually the Vice Director of the Department of Radiation Oncology, Physics and Technology of our Shandong Cancer Hospital. So he has is a wonderful medical physics in China and achieved a lot of publications and national fundings. Also have been named after a lot of China talents like Taishan School of Shandong provincial government. Also outstanding young talents in hygiene health field of Shandong province. And the national scholarship for outstanding overseas students. Also senior friends, outstanding young investigator communication projectors. So thank you, Professor Zhu, for helping us for moderate this one webinar.
Pleasure.
Also, yes, thank you our three speakers, Professor Hidetaka Arimura from the Kyushu University of Fukuoka, Japan. Dr. Shier from the technology, the Computer Science and Information Technology University of Malaysia, and also Dr. Mazen Soufi from the Nara Institute of Science and Technology, Japan. And thank you all for the wonderful work in our really first day of Chinese Lunar New Year. And also thank you for all the audience and for your participants. Our new, actually this is the last webinar, our last section. Actually, our new schedule of the webinar will start from March 14th, 2024. So it's next month. From next month, we will beginning a new schedule for the AFOMP webinar and the school webinar. So hope you see you there, and maybe lots of the speakers and the moderators. I will invite you in the future to give more to support our AFOMP by speak or moderate. So I think it's it. That's all. Thank you. Thank you very much. No further questions. We will stop today. Thank you.
Thank you very much.
Thank you very much.
Thank
Thank
you.
you very much.
Bye bye. Have a
Happy
good day.
Lunar
Thank you.
New Year.